Welcome all back. Thank you very much for participating of this last section of this first week. I think in this last section, Aurora will tell us about herself more than about exercises and teaching, because I think she has finished it already. If you have questions for her, just remember that you can write to her email. She will tell us now more about her research. So we expect a lot of questions on your side after what she presents us what she's doing. Okay, thank you, Aurora, and the space is yours.
Okay, yeah. So I just quickly put together a few slides from different talks that I've given about some of the research that I've done. So let me share that screen. Oh, and I also put together a nice collage for those of you who sent me your plots. Okay. Yes. Great. So some of you sent me your plots, and you all had some really beautiful plots with lots of colors and showing all of the stuff that we've done this week. So I thought that was really cool. I tried to use different plots from each of you so you can see that we did cross correlation and radial velocity, rotational broadening, and plotting of different spectra and different spectral ranges. So thank you to everybody who sent me plots. I had a great time doing all of this data analysis with you. And now about the research that I've done. So I went to graduate school at Boston University. And in graduate school, I studied low mass stars. And the topic of my thesis was exploring how different things like metallicity and magnetic fields and rotations, how that changed the radii in particular of low mass stars. So I've showed you a few plots from different parts of my research, but just to kind of put it together and give you some motivation as to why you care about low mass stars. This slide got a little bit condensed when I brought it in, but M-dwarf stars make up about 70% of the stars in the galaxy. So M-dwarf stars have masses between 0.3 and 0.6 times the mass of the sun for what we call early type M-dwarfs. And then late type M-dwarfs, they have masses between 0.08 and 0.3 times the mass of the sun. So these early type M-dwarfs are about 30%, 25 to 30% of all of the stars in the galaxy. And the late type M-dwarfs are about 42%, we think, of all of the stars in the galaxy. So it's a huge percentage of the stars that are these M-dwarf stars. And the problem, or what they're important for, knowing the radii of these stars, since they make up 70% of the stars in the galaxy, if we don't have stellar interior and stellar evolution models that can fit them, then we can't fit 70% of the stars in the galaxy. And also, M-dwarf stars are some of the best stars that we've been looking for exoplanets around. The radius of the exoplanet is directly related to the radius of the star. So the radius of the planet squared is equal to the radius of the star squared times the transit depth. And distinguishing between planets that are rocky and planets that are gaseous is an important part of characterizing exoplanets. So in order to know the radius of the planet well, you have to know the radius of the star well. And so we think that like the transition in radius from rocky planets to gaseous planets is about at 1.6 times the radius of the Earth. So we really want to be able to have precision so we can say this planet is definitely below this 1.6, so it's probably rocky, and this planet's above 1.6, so it's probably gaseous. And the problem is that it's really difficult to measure properties of M-dwarf stars. So like I said, they're much smaller than the sun. And they have masses that are half of that to 1/10 of the sun, but their luminosities are something like 1/10,000th the luminosity of the sun. So they're really dim, which means it's really hard to observe them. And that leads to a lot of problems. So a lot of the ways that we try to characterize the radii of higher mass stars, you can't do for M-dwarf stars. So we use long baseline optical interferometry where we can actually like resolve the size of the star for higher mass stars. We can actually see how big it is, but you really can't do that much for low mass stars. You can do it for a few of the brightest ones, but not for the really low mass ones. So we use eclipsing binaries, but the measurements so far in the literature haven't been very good. This is what we were talking about yesterday, where we're looking for the those radial velocity shifts from both stars. And so here's a plot of what we observe the radius of these stars to be minus what the models tell us divided by the model. So if the models were perfect, all of the stars would lie along the 0 line. But what we see is that there's a big scatter and that the average star is about 6% larger than the models predict. So we're trying, for my thesis, I was trying to figure out what is causing this like 6 to 15% offset. So the two things that I looked at were metallicity, so that's what we talked about today, and magnetism. And so like we saw today, metal-rich stars have larger radii. And for magnetism, we think that the magnetic fields on M-dwarf stars, I showed you when we looked at Zeeman splitting earlier, that M-dwarf stars can have magnetic fields that are like thousands of times larger than that on the sun. So we think that it basically inhibits convection and puffs up the radius a little bit. So I showed you this plot today, but just to give it again, I saw that for a given temperature, you can have stars that are 5 times larger than solar metallicity stars. But if you look at a different parameter, like I was telling you today, this doesn't necessarily mean that all of the masses of those stars are the same. So now instead, if I plot the absolute K-band magnitude, which is basically the luminosity versus the radius, there's not very much of a spread. There's maybe like a 5% spread here that correlates with metallicity. But that's only for the highest metallicity stars and the lowest metallicity stars. So in order to account for that 6% uncertainty we saw before, you would have to be getting the metallicity wrong by orders of magnitude, which probably isn't the case. And then for magnetic fields, M-dwarf stars are supposed to have very strong magnetic fields, and we've detected this through the Zeeman broadening that we talked about before. And so I did a test where I looked at the average size of stars that had large magnetic fields and were spinning quickly versus the average size of stars that versus the models. And I found that empirical relations, so that's basically relations that people made out of data, did a pretty good job of predicting the radii of these very magnetically active stars. So at most, they were only off by 5%, and it wasn't statistically significant. But the models did a really bad job of predicting the sizes of these really quickly, of these stars that have very strong magnetic fields. And on average, the stars that I was looking at had sizes that were 10 to 15% larger. And so this led us to think that probably magnetism could be the reason why these low mass stars, the models don't predict their sizes very well. Okay. So then now I'm a postdoc at Leiden University, and I kind of did a switch. So before I was studying low mass stars, and now I'm studying giant planets. But what's actually kind of cool is that I'm using basically all of the same techniques. So I got good at analyzing spectra, and I really like analyzing spectra. And I can do the same analysis techniques on the planets that I'm looking at. And what's also kind of interesting is these hot Jupiter planets, they actually have temperatures that are basically the same as the low mass stars I was looking at. So a lot of the molecules and elements that I'm familiar with from low mass stars, it's really all the same in giant planets. So that's kind of cool. And so what I've been working on, actually, when I was interviewing with my current advisor and I was showing him all of my plots of low mass spectra of low mass stars, he was saying, oh, we've been trying to look for those in hot Jupiters. And so that's what I've been working on, trying to look for some of these molecules that we see in low mass stars and that we think should be in hot Jupiters, but we haven't conclusively detected yet. And so some of these molecules like titanium oxide or calcium hydride or iron hydride are the things that I'm working on. And at low resolution, you can kind of see these like bumps here, but so this is a spectrum just from the slides before, but you can see these bumps, and it looks like they correspond to titanium oxide. But there's lots of overlapping opacities at low resolution. So this could also be overlapping with vanadium oxide or iron hydride. They all kind of have a similar shape when you're looking at just broad features. So we wanted to try to see if we can confirm some of the detections at low resolution at high resolution. And we looked for iron hydride first because it's a bit of an interesting molecule, because in brown dwarfs, they use it to trace interesting things like the surface gravity of the planet and weather and cloud formation and stuff. So we thought if we could detect it, that would be cool. But I looked for iron hydride in, how many is this? 12 different planets, and we didn't see it in any of the planets. And so these dotted lines here are showing the detections of iron hydride at low resolution. And on the y-axis, we have the volume mixing ratio. So a higher number here means that the iron hydride is more abundant. And so at low resolution, they were getting really high abundances of iron hydride from 10 to the minus 5 to 10 to the minus 3. And I did some modeling, and I figured out that I would be able to see iron hydride if it was there at abundances of 10 to the minus 7 or even lower. So what that means is there's a bit of a discrepancy from what we're seeing at low resolution and what we're seeing at high resolution. Because if iron hydride was in any of these planets at this kind of higher abundance, we should have been able to detect it pretty easily. And so what we think that means is that oftentimes at low resolution, we're overestimating abundances because there's a degeneracy with the abundance and abundances of other elements and molecules and cloud formation. And so moving forward, this should be something that we keep in mind when we're analyzing exoplanets at low resolution. And so another reason that maybe we aren't seeing as much iron hydride as we thought that we should be is because potentially iron is condensing out on the night side. And so if you remember, we have our exoplanet, which is tidally locked. So it has a day side that's always hot and a night side that's always cool. So what happens if we have this iron that goes onto the night side and then it's so cold there that it's no longer in the gaseous phase? And this is a paper by a group in 2020 where they were looking for this feature of condensation. So this is the same cross-correlation function plot that I was showing you before, except for instead of having the diagonal absorption, I've put it all into the exoplanet's frame. So I've shifted it all so if the exoplanet had no wind or any sort of dynamics, the signal should be straight up and down at 0. But what this paper found is at the beginning of the transit, they had this radial velocity shift of 10 kilometers per second. And at the end, it had 0. Sorry, it's the opposite. At the beginning, 0, and at the end, 10. And they said that this is because iron is condensing out of the atmosphere onto the night side. And so what I'm currently working on is confirming this detection with a different data set from a different telescope, and then trying to see this same feature in other planets and with other elements and molecules to see if we can figure out what elements are condensing on the night side of planets. Okay, that's kind of my introduction to my research. So hopefully I left you enough time for questions. But yeah, let me know if you have any questions about my research or about my career so far.
Aurora, thank you very much. I don't see any questions yet on the chat. Okay, now we have one. What were the difficulties you had in your student career?
Oh, okay. Lots of them.
Yeah, I will never answer that question with one single one.
Yeah. Well, to start, I didn't know that I wanted to do astronomy until I was about a little bit into my undergraduate work. So I was a physics major, and I just took one astronomy class, and then I was kind of hooked. And I was at a university that didn't have much astronomy. And so then when I applied to graduate schools, I didn't have very much astronomy experience. So the first few years of grad school were a bit challenging because I really had to catch up. But what was really great about grad school was that my classmates just, really helped me. So, and I did find that it wasn't that bad to catch up. It was maybe the first year where I felt like I was behind, but then after that, it felt okay. So there's one student struggle. But I have lots more, so.
Okay, you have nice comment here. My wife and I thank you for giving us this invaluable knowledge to bring us closer to understanding the universe and the stars. We really value it very much.
Oh, that's so nice. Thank you.
You have a question here. I would like to know what you think, or if you know about the exoplanets TOI and a number TOI-C discovered by Saint X recently.
I don't know them by their number, but if I look it up, maybe I can give you more information, or send me an email and I can give you my thoughts on it, because I don't know which exoplanet this is off the top of my head. Sorry. Okay,
here is a more personal one. How much has your motivation for astrophysics increased since you started studying astrophysics? What other astrophysics topics do you like, and what advice can you give us for our academic training?
Let's see. So for me, I think that my favorite part of doing the astronomy is really kind of doing the observations and looking at the data and discovering new things. And to be honest, I think it's less about a particular topic and more about like the discovery in general. So that's why I wasn't so set on a topic and have changed topics a little bit, because for me, I just really like observing, and I really like doing data analysis and that type of stuff. So that's my favorite part. And how much has my motivation increased? I think that this is always a question that it goes up and down, right? So there's some points where you have less motivation and some points where you have more motivation. But to be honest, like, I think that I really like my job, and I really like that I get to do something that doesn't feel like work every day. And there's lots of flexibility. So right now I can't say anything negative about choosing this career path. I mean, it's definitely hard and sometimes you feel really frustrated, but I feel pretty lucky that I get to do it. And any advice?
I will add that, if you excuse me, I will add that doing astronomy gives you the chance to travel around the world pre-pandemic time and I'm sure post-pandemic time. So it's an advantage because you know very many other cities and many other places just because you have to go there for conferences, schools, and all these kind of things. And this will give you a nice point of view.
And observing, you get to go to the coolest places. So yeah, I've gotten to go to Hawaii and Arizona and other places that, I wouldn't have normally gone. So it's really exciting.
Yes.
And any advice that I have, let's see. Yeah, I think that I've always found that collaboration is better than competition. And I would always, I think if you collaborate with other people instead of working to try to beat somebody to the same topic, it always works out better, I think. And you make lots of meaningful connections, and in the long run, you get to be part of more collaborations and meet more people and become involved in more projects and stuff. So that's my advice.
Okay, next question is, why were you interested in studying that area in astrophysics?
Like I said, I just always wanted to do observational stuff, work at telescopes, work with data. And so when I was applying for grad schools, I just looked to apply to places where they had telescope time and there were advisors who wanted to do that type of research. And this sounds bad. I didn't care as much about like the actual science topic. And then I just kind of ended up in this area, but I really do like exoplanets. I think it is like this really fun, exciting, and people like to talk about it. And I like, when you meet somebody and you say, oh, I study exoplanets, and they always want to ask about aliens and stuff. I really like talking to people about that. So I do really like this part of the job.
Okay, next question. First, they want to thank you for the lessons, and then the question is, what is your projection around the study of exoplanets in low mass stars, considering your results obtained so far?
I think that exoplanets around low mass stars is really challenging in some areas, but like really promising in others. So I think that we just have to be really careful when we're interpreting the results of exoplanets around low mass stars, not only because the radii might be slightly different than we think, but also because these stars have star spots and activity and stuff. There's a lot of chance to misinterpret results and see things that maybe aren't really there. But on the flip side, low mass stars, if we can kind of figure them out a little bit better, they offer the best chance to do atmospheric characterization of Earth-like planets. So with James Webb Space Telescope that's going up soon, the only Earth-like planets that we're even attempting to try to get atmospheric detections are around low mass stars. So it definitely offers the best chance for characterizing atmospheres, but we just have to be careful because low mass stars are a bit complicated with these magnetic fields and the star spots and the activity and all of that stuff.
Okay, next question is, what do you recommend for an undergrad student who wants to be in a similar field?
So I don't know like where you would like to do university and stuff, but I I think just going to, these days, all of the conferences are online and are usually free since coronavirus. So just trying to make some connections with wherever you want to go to university. So for example, if you would like to go in the US for grad school, the American Astronomical Society has a meeting this winter, and I think the meeting is free to sign up for, and just trying to make connections, because as with anything, if you know somebody and they recognize your name and have talked to you before, it'll always increase your chances of collaborating with them or working with them in grad school or something like that. So maybe trying to sign up for some of these meetings that are open to everybody currently could be a good idea. What else? Yeah, just trying to get research experience any way you can, even just playing around with data on your own. I think that, yeah, all of that's good.
The last question I have in the chat is, what were some of the reasons to choose the Leiden University for a postdoc position? How has been your experience so far?
Yeah, so when I was looking to apply for postdocs, I kind of wanted to do something different. I'm from Boston, and so I had done everything in Boston up until that point, and so I figured now's my chance. So I really just wanted to go somewhere different, and my husband agreed that we could go somewhere, and I said, okay, well, since you're moving with me, you can narrow down the list of the places that I apply to. And so we both thought it would be cool to go to Leiden, and my advisor who I'm working with, Ignis Snellen, he does exoplanet characterization at high resolution. And so I was kind of interested in moving towards the exoplanet route from the low mass star route. And this opportunity was kind of perfect, because all of the work I had done in grad school was high resolution characterization of low mass stars. So I could kind of make the argument, I know I don't do any exoplanets, but you should still hire me because I know how to do high resolution spectroscopy. So fortunately, he said sure. Yeah, it's been really good. I mean, it's been a bit of a challenging time to move to a new country because of coronavirus, but thankfully we got here about 8 months before coronavirus. So my husband was able to find a job before that happened, and yeah, we were able to get settled.
Yeah, the last question is also related with Leiden. Do you have advice for someone who wants to study at the Leiden University?
Oh, yes. I think if you are an undergrad or a master's student, Leiden has a summer program called LEAPS. I forget what it stands for, but basically it's a summer research program where you can apply to work with a postdoc at Leiden and do research in the summer. We are planning on still having it this summer, and it's unclear if it's going to be in person or online. We did do it online last summer. And if you kind of, yeah, I think it's a great opportunity to kind of see, hopefully we'll be able to be in Leiden. You'll be able to see if you like Leiden, if you get it. What else? I'm not as familiar with the academic system in Leiden, so I don't actually know how the application process works for master's and PhD students here. So I'm not as familiar with that as I am with the US institutions. But yeah, LEAPS, you should do LEAPS.
Yeah, so now that all of you have been in her lectures, you know that you can apply for a summer program working with her. So just try to do it. She will be happy to be working with you as well. And this is related with what she was doing of gaining research experience, because this is part of all these things that will go to your CVs. And then it will be very good to have you as an advisor. Yeah, you have many thank yous in the chat. I will add mine as well. Thank you very much for this whole week of your lectures and your exercises. I have been organizing this school for the last 6-7 years, more or less. And because the schools before were here at the university, usually you just leave the professor there and then they will teach, and I have my own duties, so I will go to do them. And I've never been attending of one of the participants of the school. And this year, because this is virtual, I have to do it. And then I am extremely surprised of how good you did your lectures and how easy it was to explain everything. Everything was super clear. Thank you very much. All the exercises were extremely interesting, even if this is not my field of research at all. I go to galaxies which are megaparsecs away from here. So this is not even close to what I do. And I found them extremely interesting. And I have been discussing this with the other professors of astronomy at the university, and they agreed with me that the exercises, working with the data, having everything public, doing this on YouTube, bringing people from other countries, is a great advantage for this school. And thank you very much for all your work and for your whole time.
Oh, thank you so much. I had a really nice time.
Remember, please, that you can contact Aurora Caselli by email. I just put it on the screen, so all of you will be able to contact her if you have more questions, if you want to send her your CVs to work with her or to try to get a summer school position over there. You know how it works. You know she's there working already. She's doing a great job. And on behalf of the organization, thank you very much. And yeah, we will see you again next week, because at the end I will invite you as well. But for this week, it was great. Thank you very much.
Oh, and I just wanted to say I'll reply all to the email that I've been sending you worksheets with the links for the Google sheet that has all of the workshops and the co-laboratory and all of my slides. I didn't put it in the slide because I figured it'd be difficult to copy down, but I'll just send it in the email.
Perfect. It's no problem. We will receive that email and we will be happy to go through it.
Okay.
Thank you all the participants as well, and we will expect to see you next week at the same time. All the lectures of this week. Next week we will start the classes on the large scale of the universe with Cristina Garcia Vergara. And we hope to see you all there as well, to know a little bit more about that subject and to do the exercises she had prepared for us. Thank you very much again, Aurora, and thank you all for the participation. And Aurora, you can read all the thanks you have on the chat. Okay, see you all. Bye.
Bye.